All right, so briefly, I just feel inclined to correct myself just because I did it wrong and I shouldn't have. For an integrator, I would have to connect my resistor and capacitor as such. In the last video, I connected them up here to the plus terminal. They would have to be connected to the minus terminal. Not that that's relevant right now, but I just wanted to make that correction so that in the future I know that I corrected it. Okay, so like I said, we're going to talk about the op-amp golden rules. And basically, there are two of them, like I said, and these two rules allow us to solve any op-amp circuit very simply by keeping these things in mind, and they allow us to set up all the equations that we need and to use Ohm's law and to use KCL so that we can actually go ahead and solve these kind of problems. Okay, so the first rule of op-amps is that the input terminals, the plus and minus terminals, we are going to assume that they're always at the same potential, okay? So any voltage that is on the plus terminal will show up the same on the minus terminal, right? So if I go ahead and take this minus symbol and ground it, then I would know that this is at 0 volts, and I would also know that my plus symbol or my plus input is also at 0 volts, okay? So it is important to keep in mind that these two symbols as the first rule, the two inputs are always at the same potential or the same voltage, okay? So that's the first golden rule. The second golden rule, no current flows into the op-amp input terminals, okay? So I might have, for example, let me just draw a little bit of a circuit around this guy. Let's say I do ground this. Actually, let's say I ground this. And let's say I draw a resistor here and I draw a resistor here. This is a typical op-amp configuration. I might have some voltage in here. And what did I just say? I said two things. So the first thing I said that the two input terminals are always at the same potential. Okay, so if this VP is at 0 volts, which it is because I grounded it, then that means that VM also needs to be at 0 volts, okay? So if I go ahead and grab my highlighter, that means that this entire node is at 0 volts, right? That's important, 0 volts. And so VN isn't going to be 0 volts, but VN is going to be some DC voltage or some AC signal, which we haven't talked about yet. But once I know VN, I can determine the current flowing through my resistor here because I know that current is going to be VN minus 0 over R, whatever my R is here. I'll call it R1, and I'll call this one R2. And the second rule that I said was that no current flows into the op-amp input terminals, okay? So what does that mean? That means that there is no current flowing into the op-amp. This terminal right here has no current flowing, right? Clearly, there is current flowing across this resistor because I have 0 volts here on one side and I have a voltage V in on the other side, and that voltage drop would be V in. So I would definitely get current flowing through my resistor, but I'm telling you as a golden rule that no current flows into the op-amp input terminal, which means I might have current here, but I will not have current here. So all the current that flows through my resistor is going to flow this way through my other resistor. None of it is going to flow into the op-amp, okay? Make sure that is clear because that is a very important concept. These two rules, like I said, if you can get these two rules memorized, which it shouldn't be too hard to do, to just memorize them. It's just the two of them. Both of these inputs are at the same potential all the time, and no current will flow into the terminals of the op-amp. Using those two rules, we can solve every op-amp circuit. We can derive the equations for the different op-amp topologies, and so on and so forth. And over here, I have this little equation, which basically is the equation that tells us how an op-amp really behaves, what it's doing. This AOL term here, that's called the open loop gain of my op-amp, okay? Ideally, that value is very, very, very large because what the op-amp does is it takes the input signal, the two inputs, VP and VM, and it takes the difference between them. There's going to be some difference here, and it multiplies it by some value of open loop gain, and that is what gives me my output voltage, right? Well, what did I just say? I just said that the difference between these two signals is 0, right? I said that they're the same value. So if this side's at 0, this side's also at 0, and so then this value would just be 0, right? So how could I ever get an output? Well, in a practical op amp, this value is very, very, very tiny. The difference between these two signals is tiny. And so we can basically treat it as 0 for the purposes of solving circuits. Although it's not actually 0, it might be like in the microvolts, and our open loop gain might be in the millions, which would give me some tangible or sizable voltage at my output. Okay, so open loop gain is something that we ideally want to be large. And in the next couple slides, I'm going to talk about ideal op amps and practical op amps and talk about the differences between the two. When we're solving circuits and when we're using the golden rules, we're assuming we have an ideal op amp, okay? And even though we know what's really happening, what's practically happening in an op amp is that we're multiplying some very large gain by the difference between the two terminals, which is very, very small, and that's what gives me my output voltage. The ideal case is that this gain is enormous. Actually, it's infinite, and that the difference here goes to 0. And okay, so without over-explaining this, I'm going to go ahead and end this video. And in the next video, I'm going to go ahead and talk about the practical op amp model, which is the real-life op amp, and then we'll move into the ideal op amp after that, which is the one that we're actually going to use when we solve circuits and when we do simulations.